Today we're going to be going over atomic orbitals. We'll be starting with the idea of the Bohr model, which we've covered, and move into something that's slightly more accurate. So far what we've covered is the Bohr model, where we have protons and neutrons in the nucleus of an atom, and then we've just said that the electrons orbit around the outside of the atom in what we call orbitals, as if they are orbiting the nucleus like planets orbit the sun. The problem with this model is that it doesn't actually show how electrons really behave. There are a couple of good things about it. It's good for describing chemical bonding, it's good for describing the emission of light, which we'll get to later in this unit, but for actually telling us what electrons are like and how they exist in the space around the nucleus, the Bohr model isn't quite right. What we use instead of that, a slightly more accurate model, is something called a Schrödinger equation, which results in pictures of atomic orbitals. Now, just an aside that will let you understand a little bit about this. It turns out that electrons are so small that we can't determine where they are or their speed at both at the same time. In other words, we can determine their location, but we don't know which direction and how fast they're going. Or we can determine their velocity, which direction and how fast they're going, but we don't know exactly where they are. It's just an artifact of electrons being so small. That's called the Heisenberg uncertainty principle, and it results in us actually not being able to define the location of electrons like this. Instead, we have to identify the probability that the electron is in any particular spot with something called a Schrödinger equation. That's like third-year college chemistry level stuff. We're not going to deal with Schrödinger equations in this class. You just have to know what the implications are. Now, as we go on into more detail about atomic orbitals and where electrons actually are around the nucleus, you may want to refer to your textbook in section 5.1, especially later on when I start drawing pictures of the orbitals up here. The pictures in your textbook are excellent and should be used as an addendum to this particular lecture. So, I want to start off with a few implications of the Schrödinger equations. And the Bohr models actually relatively reasonably well represent that. So, there are a few implications. The first implication is that electrons have energy. Every electron has energy. The amount of energy determines a little bit about where it is. So sometimes that means that we say an orbital is an energy level. In other words, lower orbitals closer to the nucleus have electrons with lower energy, and orbitals that are further away, that are larger, have electrons with greater energy. And that's actually our second implication. Electrons close to the nucleus have less energy than electrons far from the nucleus. The third implication is that the amount of energy required for an electron to jump from one orbital to the next is called a quantum. And this is actually where we get the name for quantum mechanics. The fourth implication has to do with the amount of energy in each orbital. It turns out that it's not evenly spaced. If we think about the amount of energy in each orbital, it's tempting to think like it's a ladder, where each step between each orbital is an even amount of energy, but that's not quite the case. So the energy levels of orbitals are not spaced evenly. So if down here we have the nucleus of the atom and we draw that idea of a ladder going out from it, the energy level here is relatively low. There's a big jump up to the next orbital. So this is your first orbital. This is your second. Between the second and the third, there's a smaller jump. The third and the fourth is smaller. And every single orbital that you get further from the nucleus, the amount of energy that is required to bump an electron up from one orbital to the next is smaller and smaller. But, again, the orbitals that are further from the nucleus have more energy, or the electrons in those orbitals have more energy than the electrons in orbitals that are closer to the nucleus. Now, the Schrödinger equations, I said already, give us a probability of the location of the electron. And it results in these sort of three-dimensional pictures of where the electron might be. We have given these pictures names, and so there are different types of orbitals. There are 4 types of orbitals. There's S orbitals. These are spherical, and I'll just draw it as a circle, even though it's actually three-dimensional. And there are 7 S orbitals exist. Each has 2 electrons, at least potentially. The second kind of orbital is called a p orbital. These are often described as being dumbbell-shaped. But the shape is actually more like that. And there are 3 p orbitals for each energy level. Each energy level, or excuse me, for p orbitals, there are 6 energy levels. And just like for the s orbitals, each one of these orbitals can hold 2 electrons. So that means that at each energy level, there are 6 electrons in the p orbitals. These are oriented in 3 different ways in 3-dimensional space, so these orbitals do not overlap at any particular energy level. You need to take a look at the textbook pictures for these to get a good idea of what that looks like. The next orbital level is a d orbital. These are more complex.